Hey, how's it going, guys? All right, so next example, right? We got to determine the displacements, the slopes at the nodes, forces in each element, and the reactions. Now, usually for these problems, first you start off by your boundary conditions. We'll find the slopes and displacements, which is just your displacement vector. Right at the end of the day, is just forces equal to kx. And then once you find that, you should be able to find your reactions. Then after that, we'll find the forces in each element. Then finally, we'll just draw the shear and bending moment diagram. So let's go, get started. All right, guys, so again, you start off with your K, right? Your stiffness matrix. This is a beam, so it has some stiffness, and it's transversely loaded only, no axial effects. So we're gonna go ahead and start with the boundary conditions. Again, if you know one, you don't know the other. And I'm talking about V1, Phi1, or F1Y, M1, right? In this case, look, you'll see what I mean. If you saw my previous videos, you know what I'm talking about. But in this case, like, I'll see V3. If you apply a force here, you're never gonna move this, it's fixed. So I know for sure V3 is gonna displace 0 in the Y direction, okay? Same with the angle, right? You could apply a force here, but this thing is so damn stiff at this location that if I apply a force here, this thing is keeping it so straight that the angle changes right after. It's always 0 in this case. And you should know this from statics, right? So these two are 0. We see at node 2, no matter how much force you put here, this thing is holding it here, exactly, if that makes sense. So that's also 0. That's not going anywhere. But it's a roller, so from statics, you know that there's going to be some angle of deflection, okay? So we're going to put question mark in this one. And then here, we don't know how much it's going to displace going down, and we don't know what angle that's going to make relative to the axis of interest, right? So we're going to have question mark, question mark. So just like that, because we know these three, V2, V3, Phi3, that means we don't know F2Y, F3Y, or M3. And same as vice versa. Because we don't know these three, V1, Phi1, Phi2, that means we know F1Y, M1, and M2. So let me go ahead and just assemble the stiffness matrix before it gets dark here. I don't want to turn on the flashlight. We're going to do F1Y, M1, F2Y, M2, F3Y, M3, okay? So F1Y is negative. You know what? I won't take any shortcuts, guys. Don't trip. I don't want to confuse you guys, and then this video is useless. The whole point of these videos is to make sure you guys get it. So, okay. I'm just assembling our global equation. This is step 2, global equation. In this case, EI over L cubed. In this case, L is 20 feet, okay? So from 1 to 2, then from 2 to 3, it's the same length. So that's how we're discretizing our system. In this case, EI over L cubed is gonna be 434 pounds per inch, okay? That's a stiffness. So, I mean, you got that just by EI. It's given as 30 times 10 to the 6. I is 200 inches to the 4th. And then 240 inches, okay? Don't use 20 feet. And that's how you'll get 434, right? I'm just doing the stiffness matrix. And then I'm gonna go ahead and finish it. So it's V1, Phi1, V2, Phi2, V3, Phi3, okay? And then same going this way, V1, Phi1. Give yourself some space sometimes. In this problem, it might not be an issue, but oh shit, it's a Phi2, okay? V3, Phi3. But in future problems, it might be an issue, just FYI. So I like to just give myself the space. In this case, same thing going down, right? V1, Phi1, V2, Phi2, V3, Phi3, okay? All right, in this case, we don't know V2, V3, or Phi3, as like I said, right? So we're gonna go ahead and erase them. I mean, we do know them, I'm sorry, they're 0. So I'm gonna go ahead and plug them in. 0, 0, and 0. And then since we know these, that means we don't know F2Y, F3Y, and M3, okay? Now, since we don't know V1, Phi1, Phi2, that means we should know F1Y, M1, and then M2, okay? Hopefully you guys can still see. In this case, F1Y is negative 500, so I'm gonna go ahead and plug that in. M1, there's 0 moment being applied, so that's 0. And then M2, there's 0 moment being applied, so that's 0. So let's go ahead and insert the stiffness matrix for beams 1 through 2, and then 2 to 3, right? Because 1 to 2, 2 to 3. So in this case, 12, 6L minus 12, and then 6L. Then we're gonna have 4L squared minus 6L, 2L squared. Then we're gonna have 12 minus 6L, and then 4L squared. And it's symmetrical, right? So we're gonna put 6L minus 12, and then 6L minus 6L, 2L squared. The rows just became columns. That's all that happened. Now that's for beam 1, okay? This is your matrix for beam 1, your stiffness matrix. And then beam 2 goes here, V2 all the way to Phi3, V2 all the way to Phi3. So from here, all this, okay? That is beam 2, or element number 2. So in this case, if you add it, right, that becomes double. 12 plus 12, right? So you're gonna have 24. And then let me go ahead and do that. 24. Negative 6L plus 6L, and this one too, because it's symmetrical. So that becomes 0. Okay, so these two are going to be 0. And then let's go ahead and do the other one, 4L squared and 4L squared. That becomes 8L squared. So 8L squared, 0, 0. And then it's the same, right? Pretend that's those 4. So you'll have negative 12, 6L minus 6L, 2L squared, 12 minus 6L, 4L squared. This is minus 6L. Minus 6L. It's symmetrical, right? That's all I'm doing. And I'm just filling in the rest. Minus 6L. What happened here? Oh, minus 12. Sorry. Going a little too fast. 12. And then 6L. Let's go ahead and verify that. That became 24. That became 0 because we added the negative 6L. Negative 12, negative 6, 0, 8L squared. Yep, that's right. Minus 6L, 2L squared. Negative 12. It's symmetrical, right? That negative 12 comes here. Where was I? Oh, negative 6L. Yep. 12 minus 6L. And then this one is 6L, 2L squared. Yeah, that one right there. Minus 6L, 4L squared. So we're good. And then you fill in the zeros where they belong, right? 0, 0, or everywhere you didn't get any spot, pretty much, right? So once you have that, let's go ahead and start crossing them out. V2 was 0, so that goes away. V3 was 0, that goes away. And Phi3 was 0, that goes away. And same in this direction. So that goes away. That goes away. And this goes away. So now you're dealt with 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 3x3 matrix, and that makes our life way easier. But now you go for step number 3. And equations. These are systems of equations, right? For displacements and nodes, or rotations. Let me go put rotations. Okay, so you do that, right? First one, you start with the ones you don't know, V1, Phi1, and Phi2. So you'll do negative 500 is equal to, so I'm just gonna go ahead and divide it. Negative 500 divided by 434, right? Let's go ahead and do that. That's gonna be 1.15. That's gonna equal 12 V1, right? 12 V1 plus 6L Phi1 plus 6L Phi2, right? That one right there, 6L Phi2. So that one's 1, okay? Next equation, 0 is equal to 434 goes away because you divide by 0. 6lv1, 4l squared, 2l squared. And then this one becomes 0 is equal to 6lv1, 2l squared phi1, 8l squared phi2. Okay? All right, so I just want to go ahead and write them down just to save up time. So in this case, step 4, these are the 3 equations you end up with, right? Disregard these equations for now because we don't care about them right now. We're going to do, this is equation 1, equation 2, equation 3. So we're going to do, what can we do? We're just looking at these two. Look, 6lv1, we could cancel that out just by subtracting one equation from the other. So we're going to do equation 2 minus equation 3 will give me an equation 4, okay? So when you do that, 0 minus 0, that's 0, equals, this goes away, 4l squared minus 2l squared, that becomes 2l squared phi1, right? That minus this, and then this one minus this one becomes minus 6l squared phi2. So this is equation 4. All right, let's go ahead and bubble that up just to keep it for later. Step 5. Let's go ahead and do equation 1 minus 2 times equation 2 will give us equation 5, okay? So all I'm doing is this equation minus 2 times equation 2 to get rid of the v1s again. So in this case, if we got rid of the v1s on the step 4 right here, it's good to get rid of the v1s on the other one, or else you're just going to keep going in a loop, right? So in this case, when you do that, you will get minus 1.15 is equal to minus 2l phi1 plus 2l phi2, and that's your equation 5. And I'm rushing through this because, for one, the sun's about to go in, and 2, this is just algebra. You should not do this right now. Let's go to step 6. Now let's go ahead and use these 2 equations to get rid of another variable, and that way we can solve for the other variable, right? So in this case, what I'm gonna do is equation 4, which is this one, plus equation 5. Now I see the 2l squareds will, hold on. Oh yeah, I could factor out an L divided by 0, and that's why you could add these 2, okay? Just FYI, that's what I did here. So L could, factor out an L from here and here, divided by 0, it goes away, and you're left with 2L phi1 minus 6L phi2. So when you do this, when you add these 2 equations, you'll get equation number 6, and let's do 1.15 is equal to minus 4L phi2 minus 6 plus 2L, yep, 4L squared phi2. And when you solve for phi2, you will get 0.0012 radians. And again, guys, I already pre-did these questions, so just go ahead and take my word for it. These are all verified. I will not be putting out YouTube videos that are not correct. Okay, just FYI. So now that we have phi2, we can use phi2 to plug into any of these 2 equations. So when you do that, step 7, find v1 and phi1. So using phi2, I could find phi1, and then once I have those 2, I can use any of these equations to find v1, okay? And it doesn't matter what equation you use. I'm gonna go ahead and say equation 5. I use this equation. Gave me phi1 is equal to 0.0036 radians. So we're good. And then equation 2, I just chose equation 2. I just chose whatever, it doesn't matter. You'll find that v1 will give you negative 0.672 inches, okay? And just like that, we found them. So once you find this vector, now you find this vector. In this case, f2y, f3y, m3. And we have all this, so using this same method in step 3, f3y is equal to 6l v1, blah, blah, blah. You should be able to find f2y, f3y, m3. So let me go ahead and do that one just real quick. Let me stay on this page. Step 8, find reactions. Okay, so I'm gonna do 2 of them because I only have space for 2, and I'll give you the third answer too, right? So it's F2y, the ones we're looking for in this case, F2y, F3y, and M3. F2y is the third row, which is the one that's crossed out. It's -12. Oh, you can't forget the 434. -12 V1, right? Plus minus 6L1, 6L V1, I'm sorry. At the end of the day, don't pay attention to what I say, just pay and skip the ones that are 0. Go straight to the ones you do know, right? Because those are the ones that matter. The other ones are just going to be 0. And then plus 0 feet 2, which is cool. Just closes up right there. I'm sorry, no. F3y equals 434. And then we are going to do 0 V1, 0 phi1, that's 0, minus 6L phi 2. And then that's 0, right? Because V3 0 and then phi 3 0. So cool, in that case, it's just that. Let's go ahead and do the M3. If you could see it, guys, it's getting a little dark here. M3 is equal to, I know I said I wasn't, but might as well. 0 V1, 0 phi1, 6L times 0, 2L squared phi 2. So 434, don't forget the 434, right? The stiffness. EI over L cubed. And then 2L squared phi 2. Okay. And if you do that, you will get values. F2y is equal to 1250 pounds. F3y is equal to negative 750 pounds. And then M3 will be 60,000 pounds inch. Now, before we go ahead and continue, it's good if you're doing the exam to verify these numbers, and it's real easy to verify them. You just do statics, right? Easy way to verify this is 500 pounds going down, so that means the 2 forces here going up have to net 500 pounds going up, if that makes sense. So let's go ahead and see if that's true. At F2y, you have 1250 going up, right? 500 coming down, that means this one must be coming down at, 750. So these answers make sense on the F2y, F3y. And usually when these two make sense, that means this one's gonna make sense. To verify M3, all you do is statics, right? Take a moment about 0.3. So 500 times 240, that'll give you a positive, right? Counterclockwise, yep, positive moment, 500 times 240. And then at F2, you have 1250 times, I'm sorry, that's not 240, 500 times 480, your distance to node 3. So 500 times 480, positive. Now this one's producing a clockwise moment about 0.3, so you have 1250 times 240, and that should give you your reaction at 0.3. That's how you would verify it, but like I said, with F2y and F3y, I mean, that should give you the idea if you got it or not. So next step, what step are we on? That was step 8. So now let's go to step 9. Reactions, right? So reactions, I'm sorry, hold on, we already did that step. So forces in each element. I'm going a little crazy, guys, but it's okay. Forces in each element. Okay, so element 1 is this one right here. Element 2 is this one right here. So element 1 goes from node 1 to node 2. So let's go ahead and do that. And when you do elements, it's usually between 2 nodes, and in this case there's 2 degrees of freedom for each node, so it's a 4x4. So there's a 4x1. This is lowercase f1y m1 F2y M2, okay? And that's going to equal the stiffness of the element, 434. That could change, right? In this case, it doesn't, but it could be a different stiffness for each element. And in later chapters, it gets a little confusing, but nothing we can't handle. V1, V1, V2, V2, okay? Between nodes 1 and 2. And in this case, well, the stiffness matrix from the beginning, right? That right here, 6L minus 12L, all that good stuff. Minus 12, 6L, 4L squared, 12, 4L squared, minus 6L, and then 2L squared. 6L minus 12, 6L minus 6L, 2L squared. Again, it's just symmetrical, okay? Not doing nothing crazy. Then V1, Phi1, V2, Phi2, okay? So plug in the numbers that we obtained. 672 inches. I don't like putting inches in radians. I just like throwing the actual number. Now your professor might get mad at you, but that's a you guys problem, not me. I already graduated. So, cool. Set up the matrix, right? In this case, we're looking for these four only. Where do you have these four? We know L is 240, so all this is numerical. There's no variables in here. We're done. And it's just systems of equations, right? F1y is equal to 434, 12v1 plus 6L phi1 minus 12v2 plus 6L phi1. And all these are these numbers. So let me just do it again one more time, just in case you didn't catch it. But in this case, it'd be F1y is equal to 434 times 12 times this plus 6L times this minus 12 times 0 plus 6L times this, okay? And when you do that, F1y will be negative 500 pounds. M1 will be 0. F2y will be 500 pounds. And M2 is minus 120,000 poundage. Okay, so just like that, these are our numbers. And we'll verify these. And you can't verify them just yet. You could only verify them as soon as you're finished with all elements. In this case, 2 elements, all right? So I'm gonna go ahead and do the same step, but now for element number 2. 2y M2, F3y M3. Okay. And again, the flexural rigidity is the same. Let's go ahead and do V2, Phi2, right? This one's between nodes 2 and 3. So that changes. V2, Phi2, V3, Phi3. Then same thing, 12, 6L minus 12, 6L, 6L, 4L squared minus 6L, 2L squared minus 6L, 4L squared minus 6L. I'm kind of all over the place, but I'm just copying the same matrix from here. And let me tell you guys something. This matrix is not the same as if you were to take this piece right here, okay? You cannot just take 24, 8L squared 0 and just get this piece. And then for the next one, this one. It's not how it works. You got to redo the stiffness matrix. So now the displacement vector for this one, right, is just forces equal to kx. That's all it is. In this case, this one's a lot easier. 0.0012000. So V2 Phi2, V3 Phi3. So all of these are 0, right? You go to V2 0, and that's not 0. This is 0. This is 0. Boom, boom, boom. So in this case, it's just 4L squared for everything. F2y, once you do all that, at least I think, right? V2, 0. Yeah, that should be it. So in this case, we just care about this one. F2y is equal to 4L squared V2. And yeah, that should be it. Straightforward. So F2y, when you do the math that we've been doing this whole time, 750 pounds. M2 is 120,000 pounds. Inch. And again, these numbers have been verified, so just take my word for it. F3y is negative 750 pounds. And then M3 is equal to 60,000 pound inch. All right, so check it out. To verify these numbers, when you sum all of the force 1s, force 2s, force 3s, force 4s, if you have any, 5, 6, 7, whatever, when you add them all together, they should equal your big reactions, okay? The ones that we found here and the ones that we got here. Well, we already have all 6. Let me show you what I mean. F1, add all the F1Ys. In this case, nope. Only have one, right? So that means this one should be equal to the F1 here, negative 500. When you do the same with M1, right? There's no other ones, so that means M10 should be the big M10. And yeah, it's true. F2Y, 500 pounds. There's another one here, 750. Add them both together, that's 1250. Boom, that's what we got here. M2, negative 120,000, positive 120,000. 0, boom, that's good. F3Y, there's no other ones except this one, negative 750. Boom. And then M3, 60,000, that's the only one. Boom. So that's verified. That's how you verify that, okay? Once you do that on the exam, you'll know you're doing it correctly. And then finally, the shear and bending diagram. Oh, everybody loves these, man. So, I don't know. There's a lot of ways you could get the shear and bending. My professor never cared. I did it my favorite way when I was in statics, right? Bending moment diagrams. Final step. And go ahead and just finish it up, right? This is shear, and then I'll do bending here, okay? This is how I do it. And again, there's no right or wrong way. There's lots of ways you could get the shear and bending diagram, but this is how I did it. So we start here, and this doesn't mean it's fixed, okay? It's just an axis. That's right. V, X. In this case, this is in pounds. This will be moment, pound, inch, and then along your beam, along your X direction. So 500 pushes down, nothing. 1250 pushes up, nothing. 750 pushes down, right? Again, 500 pounds going down here. This reaction's 1250 going up, and this one's going down, negative 750. So that means that's what our bending diagram is going to look like, right? So let's go ahead and do 500 here. Let's go ahead and do 750 up here. And let's go ahead and assume that's halfway throughout the beam. So we're going to go here. Boom. 1250 pushes up. So we go all the way to positive 750. Nothing happens. And then 750 brings you back all the way down. Okay? And that should work if you did it correctly. You should always end up back at 0. So this was 240 inches. This was 240 inches. And this is how I solve for the bending diagram. So let's go ahead and shade the area, right? Just to make it look nice. You don't have to, but whatever. I like to be creative with it. Okay, now to get the shear, the bending, use this to get that. In this case, look, we have a negative 500, okay? Negative 500 times 240 will give you negative 120,000 pounds. Inch. Pound times inch, right? This one is 750 times 240. That's 180,000 And you're probably starting to see the numbers. It kind of makes sense, right? 120,000, you see all that? Look, here's how it happens. And this is going to be halfway throughout the beam. I don't know if something's going to happen there, but I mean, I do, right? But you shouldn't, you wouldn't, is what I'm trying to say if you're in the exam. In this case, we start at 0, and our slope, since it's a negative 120,000, that means our slope is negative. Take the integral of this, right? For a straight line, I'm gonna do it over here. For a straight line, if this is your function, your integral is either like this or like this, right? If it's negative, if this line is -5, then, I mean, or it could be 5, right? I mean, it doesn't matter. You don't know where you're at. So it could be 5x or -5x. Same thing here. So in this case, we know it's negative. And so we're going to go down. So we're going to go here. We are going all the way here. Okay. And this value is -120,000. Boom, boom, boom. It's pound inch. Then what happens at this location is, check it out. Moment is 0, right? So nothing happens, nothing is pushing up. If there was a moment here, then something would have pushed it up or down. But since it's 0, nothing happens. But what happens at the shear diagram? You have 180,000 going up. So now it changes direction, right? Because at the halfway point throughout the beam, which is here, now you have 180,000 going up. And it's a positive because look, we're above the 0 mark, okay? That's a positive. So that means this slope is gonna be 180,000, okay? So now we're here, 180, if you were at -120 and you went up to 180, well, now you're at 60, okay? So that means I'm at 60, I should be at 0, and boom, what do you know? The 60,000, when it's positive, when it's counterclockwise, a counterclockwise moment will push you down. That's what I hate about these courses, right? You got to know all this stuff, but when you're drawing the shear, the bending diagram, counterclockwise pushes you down. I mean, this whole time we've been taught that counterclockwise is positive, right? So you might think to push it up even more, but no, that's not the case when you're making the diagram. So in this case, 60,000 pushes us back down to 0, and boom. So there's a positive moment. This is a negative moment. And let me go ahead and just give you guys some quick knowledge. As a structural engineer, when you're doing this kind of stuff, the reason you do all this is to see how you're going to design your cross section. You do this diagram and it tells you, hey, look, this is my area of concern. This is where 120,000 pound inch moment is happening. So I have to make sure I design that beam to withstand 120,000. I got to choose a material, choose a cross section. And if you're a really good engineer, you're going to take into account the manufacturing processes. How are they going to build it, right? You don't want to build something that's going to be crazy expensive to build, right? So, I mean, it's a whole new gang, right? It's a whole new world of things to take into account. But the reason you do these problems in school, guys, is to take into account how much shear is happening. In this case, 180,000 pounds is max shear, and -120,000 is our area of concern. So you're going to design, if you were designing a beam, right? I don't know, an I-beam. Let's take an I-beam, for example. Well, we know shear loads your webs, okay? So as soon as vertical shear is introduced, this could be the cross-section of an aircraft. This could be a beam in a building. It could be anything. But you need to make sure your webs can handle 180,000 pounds, depending on how much your height is. And just to keep it very simple, if this is 20 inches in height, divide 750. This is a moment. Divide 750, which is your max shear, divided by 20. That's going to give you some number, right? I don't know off the top of my head. 37.5 maybe. 37.5 pounds per inch of shear flow is happening in your beam. So you have to design that web to withstand that. And you might also have to check for buckling, things like that. And when that shear goes into your beam, it loads your caps. And that's what's fighting the moment. So you need to make sure this section, and this section too, technically, right? But sometimes you can, in industry, these things are very thin wall, that this really is your bending material. So you need to make sure this section up top is withstanding, it can withstand 120,000 pounds of moment, at least at this location, right? this could be a whole beam, and it doesn't have to be continuous, right? The beam could be very beefy at this location, so we could have this. Shit, I messed up. I-beam. So it could be very beefy. Let me just go all the way out. It has to be, the caps have to be beefy here to withstand this much bending moment. And then at this location, you need 750 pounds of shear flow. So this web, at least if you were to write this halfway throughout the beam, these webs on this section of the beam have to withstand 750, while this one only has to withstand 500. Then right here, these caps, which is the top flanges of your beam, right? The top flanges here have to be able to withstand 120,000. Once you get here, these caps don't have to be as thick. And you might be thinking like, well, yeah, I mean, how are you gonna make a beam with a different cross section all around? And you're right. I mean, in some applications, it's better to just buy the whole damn beam. And as long as it withstands this section, it shouldn't be an issue. But that's typically for buildings, right? Because you don't care about weight in a building. You just want to make sure that thing doesn't fall. But what if you're designing an aircraft and the wing, right? I work on, I mean, I can't tell you guys what I work on, but let's take the B-2, right? The B-2 is a bomber, and it has a triangle shape. So I imagine that the wings are mated to the center body right here. I've never worked on the B-2, by the way, but I'm just kind of thinking logically. If you attach wings to the B-2 to a center body, if it's not joined this way, right? Sometimes planes in general, like a Boeing 737, they have different types of joints, but some planes can be bolted on. Some planes are part of the fuselage assembly, but this is an I-beam right here. It can be an I-beam, right? Who knows? But the thickness of the caps could be very thick here, very thin here, thin here. It depends on how they design this thing. And that's why these diagrams are important, and that's why you guys should really know what you guys are doing when you guys are taking these classes. Every problem you do, start looking at it that way. Hey, look, I found my bending, I found my shear. How am I gonna design a cross section to do all this, right? And in this case, they already gave you E and I, meaning they already have the cross section and they already have the modulus, the material, right? So this is more like a check. But let's assume you didn't have any of this, right? Let's assume your employer came up and said, hey, design me a beam that can withstand this much pounds of shear and this much moment. And you as an engineer, you got to put on your smart cap right now and be like, all right, this is how I'm going to do it. And this is what I'm going to look out for, and boom. So yeah, guys, that last part wasn't really necessary, but it's cool to know what you guys are doing. These problems are very good if you know what you're doing, right? And, you know, in school, they don't teach you any of this. It's just, you got to figure it out. I didn't know it in school. I only found out about it here at work. I work with a level 6 structural engineer, and that guy gets down. He could design planes like nothing. But you know what? That's it. That's the answer. Take my word for it. The answer's correct. But hopefully it wasn't too fast, and hopefully you guys can read it. But yeah.